Okay, so today we'll talk about compressive sensing. This is typically a guest lecture by a professor here, Aswin Sankaranayan. He teaches deep learning, intro to deep learning. So I took his course. I really liked it. So I encourage you to do the same. A lot of this class is about linear algebra. So we have this fundamental system. X is the input and Y is the output. And a system is like unknown, right? You don't know what it's doing under the hood, but it spits out a Y. So is this system linear, right? And the main question we want to see is, given some output, right? You don't know about X or the system, but you know about the output. Can you recover X? This is like a fundamental phenomenon that happens in the real world. Like to give an example, sometimes you might be like gathering data, like from a signal, like the Nyquist theorem, you're just gathering, but you don't really care about your measurements. You care about what it was originally, right? So if I'm gathering sample sound of a guy in a movie, I want to hear what he said at this from start to finish. So this is a fundamental problem in signal processing. Is I have some output. It's probably low dimensional, and we want to recover the large dimensional X. So we want to understand this right side. What did you do in the what was the matrix you hit it with, that feed thing, and what was the input that was fed into it? X. It's kind of like you have Y equals mx plus b, and you want to know what m and x are. Right? So now let's get into the types of matrices and what kind of problems this is. So what were the three kinds of matrices? Do you guys remember? There was like full rank was one of them. What was the other two? Undetermined. Okay, what was the other one? Overdetermined, right? So in full rank, the diagonals were all one. So there was only one solution, right? In full rank. That's why full rank is like the desirable option sometimes, because you want every variable to have a value. But that's not the case in real world scenarios. You either have underdetermined or overdetermined, right? So what happens if overdetermined? Like, is there a solution to the problem when you have an overdetermined matrix? No, right? Because it's tall. Like, I won't draw it. But if you have a tall matrix, like the opposite of this, the only, the rank it can be is at most the column length or the row length. So not all the columns will be filled out. So that's why overdetermined matrix will not have a solution, but in underdetermined, what's the case?
Infinite solutions.
You have infinite, right? You have infinite solutions. So in underdetermined problems, you have infinite solutions. So now becomes the problem that which one do you want to pick, right? You want to pick one that maximizes a norm. You want to pick one that minimizes a norm. There's infinite, so you can choose as many, choose the one that you want. So this is the problem in signal recovery, sparse recovery, that you have some large dimensional input X right here, and then you have an output, and they're both just tall vectors, right? N by one and M by one. But your M is very small, right? The measurements you're doing are very small. And so you don't know the phi and the X. But you know that X is a large dimensional, so this is a undetermined problem. You basically want to find the right phi and the right X that solve this problem. So now I'm going to show you a phenomenon. The professor can talk about this too, that in terms of real life, low frequencies will always dominate. And this is going to be a fundamental idea in compressive sensing. If you look at this picture of a turtle, you can see that mainly there's low frequency colors, right? We have blue, like the aqua blue. We have sort of like a turquoise green. And when you see this image and there are those white spots, you can kind of fill in your brain that, oh, like that white spot in the top right is probably like blue, right? The aquatic blue. It's either going to be red or it's going to be green. I know from my real world knowledge of aquariums and turtles that that's going to be a blue upper right corner. Same with this. This might be an ambiguous image, but you can use your best interpretation of real life, see what this is. This is probably a man in a field. And then we also have super resolution. This is an application of compressive sensing. So do you want to talk about that, Professor? The low frequencies dominate in this world.
So you go ahead. This is something we've already mentioned in class, right? That, for example, if you look around you, most of the scene is just uniform shade or slowly varying shade. Yeah. Actual features which comprise fast changes are very few. So whether it's images, whether it's sound, whether it's any kind of structured data, it's dominated by low frequencies. Just the nature of the world. Anyway, go ahead, Adnan.
Okay, thank you. So yeah, low frequencies will dominate this planet. Okay, so like all of us on Earth, it's just what is it, blue, and then I have this gray right here. So these are just low frequency colors. So what that means is that in this world, we deal with sparse items. When you guys do research and when you guys get into signal processing, you will see that most things can be represented in a sparse domain, right? If you guys heard of the fast Fourier transform, that's what that does, is it turns very large objects into a very sparse domain because only few frequencies will dominate the medium. Like, let me give an example. If I get a picture of my phone, this classroom, right? Low frequencies are gonna dominate. My shirt color, this pink color on the chair, and all that. So only few frequencies would out of all the frequencies, only some, the low frequency ones, will spike up. So that's what happens in your phone actually. That it can't store a 4K photo. It converts it to an FFT and stores that sparse information instead. Is there a question? So that's just a thing for you to think over. That high frequencies like colors you don't see often, they don't really dominate most of the scapes you see. We have the low dimensional, sorry, not low dimensional, the low frequency that dominates. So let's go over, let's go to the whiteboard. Yeah, a little bit. And then if you guys have questions, you can unmute or ask here. This is just a lecture to get your brain spinning. There won't be any polls or anything like that. Okay. So like I was saying, like on your phone, you know, you take a 4K photo. A 4K photo, I think it's like a cube, right? I don't know. Does anyone know it's like a cube, a 4K photo? It has like 1 million pixels, 4K photos. But the convenient thing is that pixels, the low frequency will dominate. So when we convert it to a fast Fourier transform, what will happen is if we have the frequency, that's what that x-axis is, only some will dominate. So this becomes a sparse representation. And so the reason I'm talking about sparsity over and over again is we had an undetermined problem But now, since nature reflects sparsity, we want to see the one that is the most sparse, right? So I just said three things. We have infinite number of solutions, that's number one. We want to see the one that is the most sparse, that is number two. And the reason we care about sparsity is because that reflects the real world domain, like I showed with that image photo. And that's what we want to do. There's no quiz, don't worry. No polls today. Okay. And then sparsity is, just to make it clear, sparsity is the number of non-zero elements in a vector. So like if you've ever seen those like big mass things like 1, 1, 1, 0, 0, 0, that's like a sparse vector because only 3 of them are 1, everything else is 0. Okay. What is that? This, yeah, we'll talk about it. So what do you guys think this is? Let's simplify. Okay, by a computer. Okay, what else? He's on the phone. Yeah. He's on the phone. Okay. You'll be surprised with images.
Wearing a watch.
He's wearing a watch. I can't tell. Oh yeah, this thing. Okay. He could pass as an airplane pilot or something. But no, he's just talking with his shoe, and there's a trash can right in front of him. But what you guys did was you used your previous knowledge to fill in what this is, and that's the whole idea of compressed sensing. Is we do sparse recovery, but we use the characteristics of the data to infer what it is. And this also shows how tough this is because there are many examples, right? Yeah, and I don't even get why that poster is there. No polls, yeah. This one, have you guys seen this? Like, I think it's a video, I'll play it, but he's here, but then when he walks here, he becomes shorter. He becomes, I think, as tall as that clock. This is an optical illusion. Because as you walk in like it's one of those things where the hill is up, but it's actually going down, one of those optical illusions. That's what this is. These are just showing you that the real world phenomena, we know it may not be what it is. So compressive sensing is a very touchy subject. And let's complete the sentences. The first one, we already know, I don't need to say it. And the second one, give me freedom or give me death. Second one, hey, I'm solving non-determinate linear system. Underdetermined, I think underdetermined linear system. So we're using our real world knowledge to solve this, right? Same thing here, we almost do. You have to respect the rules of the matrix.
Brute force.
Brute force, there's recursion too. This is popular in the recursion questions on interviews. And we did this before. So let's see. Okay, so I think I was just illustrating an idea. But the thing is, we want to solve the undetermined systems by using additional structures. So, like I said before, undetermined means that there's infinite number of solutions, and we want to find the one that is the most sparsest, right? So we need to impose constraints. So there's, let's just recap. So we have a signal of interest, we want to find this out. X is Rn, and then we're already taking observations. When we get to our careers and everything, we're going to take observation. We won't know anything about the stream, we just know what's coming out. So we want to know what these two are, phi and x. So now, like I said, this is the problem that y is a low dimensional representation. Phi is an m by n, so it's not a square matrix, it's a y matrix, and x is a tall vector. and we don't have a unique solution. So this is what sparsity means. You see this X vector, 3 of them are colored, but the rest are not. Those are zeros, right? So you can think about it. That's like selecting the 4th and the 7th and the 4th to last column, because we go like that, right? So we're selecting like a subset of the columns of phi. So when it's not full rank, this is another thing you should know, is that you're gonna have to compromise with information loss, right? We don't have a full rank matrix. If we did, then we'd get a perfect reconstruction, but we don't. But the thing is you're only interested in recovering sparse signals. Has any of you guys heard of the L0 norm? What is that?
But I think we're staying there with 0 and then it's counted number of answers.
Yes, L0 norm is counting the number of non-zero elements. So if I told you to minimize an equation with respect to L0, do you think that's easy? Like what if I said
We could not, we can't take a gradient of that, so you would need to use like what was it called? Combinatorial.
yes, exactly. So this is a what's it called? NP hard problem. So now I could end the class here and say that this is an impossible problem. This is you're trying to minimize a non-convex function, L0 norm. So should we just end it? No. There is a technique we can do called L1 norm minimization. So I'll get into that later. But we have to enforce 2 key ideas. So the first is that we need to have phi. Phi is the mapping, and it needs to be invertible. It's not a full rank, but it has to be invertible, right? But a full rank matrix, non-full rank matrix is not invertible. So we need to understand what to do. So now comes, have you guys heard of like isometries? Isometries? If you guys ever took linear algebra, you probably heard this term.
Symmetries, I heard the abstract or
What do you think it is?
things are kind of the same. If you
Somewhat. We are, what do you know? So we're going from Rn to Rm, right? So there are 2 different worlds. Like it's like an alien, like it's a different planet, right? So when I convert to another world, right, the points are going to another space, I want the distances to be same, because if they're not, this projection or this matrix multiplication can screw up the original readings. So this is what an isometry is you have an efficient mapping that gets that preserves the distance, right? Picture these are like close together. Then I can't trust the transformation because it didn't preserve the original distance. There will be this thing called, I think, TSNE. That's what that does. That's not part of this lecture, but TSNE will preserve the local neighborhood relationships. So this is what we want. We want an isometry that preserves the distance. That's what that second point is trying to say. So, sorry. Because we're not full rank, we have to compromise a little bit. And that's what this restricted isometry property says. That let's take a number k, like number of k non-zero elements, will give us slack. And if it respects this constraint, then it is an RIP. Not that RIP, but it is a restricted isometry property. So I'll explain on the board. I screwed up this table. So we have y equals phi x, and phi is a tall or wide, matrix, and x is a tall matrix, and Y is a low matrix. This is M, this is N. No, this is M, sorry, that's it. And this is N by N. So you don't really need to fully digest that formula. But what that's saying is if there is, there probably is a subset of this matrix that almost behaves like a full rank matrix. We're gonna compromise because this whole thing is invertible. But if we have the matrix in a RIP, like it satisfies the restricted isometry property rule, it's okay for this problem. So yeah, that's what that's saying.
This don't change very much.
So basically what I'm trying to say is that you can see, right, we're subsetting those columns. So we want to make phi in the RIP form because that will make, that's like the first criterion. It's RIP, it'll preserve the distance, it'll get a good reconstruction. And the RIP form will also satisfy the invertibility. So guess what distribution is RIP? He said it before. Gaussian, right? Gaussian distributions are in the RIP form. So that's why Gaussian distributions, they will be desirable in this case. So in this problem, if this were in the real world scenario, phi might even be a Gaussian distribution based matrix. And some of the things people may ask is, what's the right M, right? What M do I choose? You can just take K log N over K. I don't know the proof, but this is like a sufficient M. So M is like the dimension of that you're trying to sample. Okay, so now comes the second idea. We have, the first one was about finding the right, getting the right RIP phi matrix. Now the second one is to use sparse primes. This is what I've been saying the whole time, that you have an infinite number of solutions, and now you want to find the sparsest one. So if you look at this plane, right? I'm going to show something. That plane is like this, right? Let's just make it 2D for now. So if I want to find the sparse matrix, I can use the L1 norm. And then I can extend this L1 norm to here. And this is just two-dimensional, but this is sparse, right? This is technically like K0 because it's on an intercept. But this is 2 dimensions. If this were like n dimensions, then all the other n's would be 0. So this is another thing you should memorize, that minimizing the L1 norm with RIP is the same thing as minimizing the L0 norm with RIP. So we basically made an impossible problem, convex and easy to solve, because RIP matrix, the L1 and the L0 norm minimization will be the same. I think the professor can prove that if he has the time, but I'll just say it. Okay.
Just continue, but if anybody wants to take it to Piazza, we can not.
Yeah, so definitely ask questions on Piazza. But originally the problem was argument of x0, right? But that is NP hard. So if we make it x1, the L1 norm, and we just do that diamond technique I showed you, the L1 norm is a diamond on a graph. So we can kind of extend it to that plane of infinite solutions. And that is our sparse vector. So, yep. And yeah, this is a short lecture. You already know about the Nyquist, right? You have to sample with double the amount. You should always remember this theorem. And I'll show you some applications. This is the normal video. And then when you compress it, you get this. So this was done with exactly the technique we showed. We recovered this using the sparse techniques. And then this is also used in MRI and also motion flow models. So this is a short lecture, but sparse recovery is like the heart of signal image processing. And everything with images and mediums, sparse recovery is there because this world is a sparse world. So yeah, that's it. Shortest class this semester.